And then we will go ahead and draw. Let's go ahead and draw the vector in purple here. And let's draw it in quadrant number 1. And let's make it easy. Let's draw this at 45-degree angle. So the vector A has a magnitude of 13. Could be meters per second if it's velocity, could be newtons if it's force, which we'll talk about later, could be whatever for a magnetic field, whatever. It's some arrow with a unit of 13 long, and the angle here is 45 degrees. Now, before we do anything, because you know that this is at 45 degrees, once we calculate the x portion of the component and the y portion of the component, because it's a 45-degree angle, the x and y components will be equal because the thing is splitting the difference. You see I've drawn it splitting the difference at 45 degrees between x and y. So the x and y component we strongly suspect should be the same. So what you need to do is, we're going to draw a picture at the end, but I want you to get used to visualizing it in your mind, okay? What we want to do is we want to take this vector and want to break it up into a vertical component, and then separately from that we want to break it into a horizontal component, right? So how much of it is this way and how much of it is this way? So in order to find the horizontal component, remember, horizontal component deals with cosine, the adjacent side of this triangle here. You got to envision in your mind a triangle here like this. So to find the AX component, right, we just take the hypotenuse, 13, which is the length of this thing, 13. And when we're trying to find the X component, that goes along with cosine. Cosine of what? Cosine of 45 degrees. So you don't really need to redraw the triangle all the time. You're going to get used to the idea of multiplying here. You chop it with a cosine and gives you that horizontal projection. So that AX is going to be equal to 13. You take the cosine of 45, you get 0.707 in your calculator. That's a truncation. It really goes on with more decimals there. But the AX component is 9.19. 9.19 what? Well, it depends on, if it was meters, it'd be 9.19 meters. If it was meters per second, it'd be meters per second. I haven't even given you any units here, so we're just going to leave it alone at 9.19. And then we're going to go over here, let's switch colors and find the y component. A sub y vector, what is it going to be? It's going to be the length of the vector itself, the hypotenuse 13, and we're chopping it to find the y component, so that's going to be a sine, the opposite of this angle, sine of 45 degrees. Now when you go in your calculator, and you might remember this from trig also, the cosine of 45 and the sine of 45 is actually the exact same thing. Why? Because this angle exactly bisects the x and the y axis, so the sine and the cosine give you the same thing, 707. So what you get for y, AY, is exactly the same thing as we had before, 9.19. Could be meters, whatever. So our prediction was true. When you get a calculator and multiply all these numbers together, the x component, which is the projection along the x-axis, and the y component, which is the projection along the y-axis, are the same. The only reason they're the same in this problem is because 45 degrees exactly splits this 90-degree angle in half. If the angle were anything other than 45 degrees, then the x and y components would be different, as you might expect. So the next thing we want to do before we do anything else is, we don't always care to do this, but let's just check it. If this does form a right triangle, then the Pythagorean theorem will always hold. And the Pythagorean theorem is, as you know, c squared is a squared plus b squared. The hypotenuse in this case is c, so it's 13 squared. And we're asking ourselves, is that 9.19 squared plus 9.19 squared, yes or no? Now, when we do that on the left-hand side, what we're going to get is, or on the right-hand side, is, 13 squared. It's going to be 169. And we're asking ourselves, is that equal to this squared plus this squared? That's going to be 84.46, 84.46. And when you add them together, 169 is equal to 169. You might have a little decimal here left over as a rounding error because of the way we rounded here, but it's going to be so close that you can basically say they're the same. So this does form a right triangle, so we are confident that our components are correct. And if you absolutely wanted to drill it home, which here in the beginning problems I want to do this most of the time, you can then draw this triangle explicitly. You can say, well, what I'm saying is this is x and this is the y direction. What I'm saying is that if I walk along x, let's go and change to purple. If I walk along x for 9.19 units, like this, 9.19 units to the right, and then I walk up the exact same amount, 9.19 units up, because this is the x component, this is the y component, then what I actually get in the end of the day, let's do it this way. This is ax, this is ay. So what happens is if I connect them like this, when I do my vector addition, then this is a. So just showing you that the a vector is decomposed into an x component and also in a y component. In this case, they happen to be the same length because of the fact that we chose 45 degrees to begin with. So now we've done a vector in quadrant 1. Let's go and draw a vector in quadrant 2 and see what is different. And you will find that there is some things that I want to point out when we have a vector in the second quadrant. But the math is really all done the same. So we have xy plane, as always. Here's x. Here's y. Let's go ahead and draw the vector. We're going to draw it over here like this. And then we're going to say that this angle measured, again, it's measured from the x-axis, is 120 degrees. Remember, this is 90 degrees straight up and down, so we've gone a little bit past that to 120. And then the vector here, we called it a over there. We'll just call it b vector. And it's equal to a length of 7. So what we're saying is the length of the arrow is 7, so really I drew it the same length as this one. It should have been really a little shorter. It doesn't really matter. But the length is 7, and the angle is 120 degrees, which pushes it into the other quadrant. When a vector is pointed a different direction, it doesn't change the math. You do everything the same, but the conclusions, I'm going to point a couple things out to you just to make sure you're aware. So how do we find the x component? Find the x component first. How do we do that? Well, if you envision a little triangle here, same sort of thing. When you take the cosine of this angle here and multiply it by the hypotenuse, it's going to chop it and give you this x component. So you take the hypotenuse and you multiply it by a cosine of, what do we have, 120 degrees. All right, 120 degrees. So that's going to be equal to 7 times negative 0.5. When you go in your calculator and take cosine of 120, you get negative 0.5. So the x component is going to be negative 3.5. All right, so keep that in your mind. Let's do the next guy, and then I'm going to draw a conclusion for you here. What is the y component equal to? It's equal to the same hypotenuse, 7, but now times the sine of 120 degrees. So you use that angle as measured from the x-axis, which defines the vector. And so what you'll get is 7 times. What is the sine of 120? 0.866. Of course, there's more decimals. I'm truncating it here, but you get the idea. And when you multiply that by 7, you get 6.06. All right. So what we have shown is that in this case, the y component of this vector points up because it has a positive value. It's pointing in positive y. Makes sense because the arrow is angled upward. It's going in the positive y direction. But the x component over here actually has a negative sign in front of it. The negative sign comes from the cosine operation. When you stick a cosine into your calculator and hit the button and do the, if you remember trig and all that and the unit circle and how it's all defined, the cosine operation for an angle bigger than 90 degrees gives you a negative number. The negative sign came from here, and that's because the projection of this thing, if you shine a flashlight down onto the x-axis, gives you a negative answer because then the component would be pointing this way. So what this is telling you is that you have, if this is motion, like 7 meters per second up to the left, what it's telling you is you have 3.5 meters per second left along the negative x direction, but you have a larger velocity, 6.06, going in the y direction. So, and that makes sense. More of it is going up as compared to how much of it is going this direction. So if you wanted to be absolutely explicit about it, you could draw yourself the guy here. We could redraw the vector right here. And then what we could do is we could do dot, 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 dot down here. We could do dot, 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 dot over here. And then what we could do is label it and say the x component here, bx, is equal to negative 3.5 meters. And then we can see here that the projection along y would be this guy right here. And so b sub y, what we're saying here, is equal to 6.06, which is obviously a larger number than this one because this is taller. So it all graphically makes sense here. And of course, the vector b is what we labeled here. So why am I mentioning all this stuff? Because I guess I want you to know that when you calculate vector components, it's very common for you to get negative components. So if you get a negative x component, it isn't like weird or crazy. It just means the vector is tilted that way, so it has a component in the negative x direction, right? And then if the vector is only in the positive axis here, or only in quadrant 1, it has a positive x and a positive y. If the vector is in quadrant 2, it has a negative x and a positive y. Bonus question, what do you think is going to happen if the vector is down here, pointed this way? Well, you're going to have negative x and you're going to have negative y. Bonus question, what's going to happen if you have a vector over here? You're going to have a positive x, because it's angled that way, but a negative y. So depending on which quadrant the vector is pointing in, you should expect and get used to thinking about what component you actually are going to have. If it's pointed down in any way, you're going to have a negative y component. If it's pointed to the left in any way, it's going to have a negative x component. And then the opposite is true if it's pointed in the other direction. So let's go ahead and do a quick example when that vector is pointed into the third quadrant there on the lower left-hand side. I guess I should say that I guess I'll do it real quick, so I have it in my notes. C squared is a squared plus b squared. Just checking yourself. This is a right triangle, the length of which hypotenuse is 7, so 7 squared. A squared is negative 3.5, but when you take a negative and square it, you end up with a positive number. 6.06, square it. If you get this, you'll have 49 here. And on the right-hand side, when you square those things and add them together, I'm just trying to make sure I got the right numbers written down here. What you'll get over here, when you square negative 3.5 times negative 3.5, what you would get is 12.25. And then this guy right here will be 36.72. When you add these two together, you also get 49. So the Pythagorean theorem is verified. So anytime you find vector components, you always should get the sides of a triangle, which are going to obey the Pythagorean theorem. It's a good check if you want to check yourself. All right, the next thing is we have an axis like this. X, Y. Let's go ahead and put our vector in place. We're going to do it in quadrant 3, so let's go down here and draw our vector right here. So we'll say it's equal to length of 9, and let's say the angle as measured by the positive x-axis goes over here, being 200 degrees. Don't be worried that an angle goes all the way around like that. That's what you learn in trig. When you are in 4th or 5th grade and you learn about angles, you're always talking about those acute angles in the triangle. Sometimes they get larger, but when in trig, you can measure an angle all the way around to 360 degrees and then back around and again and again and again. So here we've passed 90, we've passed 180, and then we went just past that to 200 degrees. That specifies the direction of that vector. But the math is exactly the same. To find the component along the x direction, what do you think it is? It's going to be the length of that hypotenuse times the cosine of what? 200 degrees. All right? It's the hypotenuse. Cosine chops it into the x direction, right? That's what I keep telling you. So 9 times, what is cosine of 200? You'll get negative 0.9397. I truncated the decimal, obviously. So the x direction component, when you multiply this by 9, you get negative 8.46. meters or whatever you're talking about. Notice it's pretty close to 9. That's because this vector is very close to the x-axis. So most of the vector is going to be lying in the x direction. And notice it's negative. That makes sense because the arrow is pointing in the negative x direction. So you should have a negative x component. The projection should be going along this way. Now, the y component is what? 9 times, and to chop it in the y direction, it's the sine of 200. All right? So then you get 9, when you take 200 and you take the sine of it, you get 0.3420. And so the y component is going to be equal, when you multiply by 9, negative 3.08. Actually, there's a small mistake here. I just didn't copy it in from my notes. You take the sine of 200, it's negative 0.3420. So when you multiply it, you get negative 3.08. So that's all correct. So the negative signs that you get that tell you the direction of the components, they all come from the sine and the cosine function. Because when you go back to trig and you define sine and cosine and you go back to the unit circle and all that stuff, the cosine and sine function always give you the correct sign so that they're defined in terms of the projection of these vectors from the unit circle onto the axis. So if it's over here, it's going to give you a negative x, and it's also going to give you a negative y because it's projecting in the y direction. So you see you have most of the vector in the negative x direction, but some of it, a smaller amount of it, existing in the negative y direction. So when you add both of them together, vectorially, the y component points down, the x component points to the left. All right? So if you wanted to absolutely drill it home, then you would have, I'll draw little dotted lines. This guy would be cy, which we just wrote the answer to, and this guy would be c sub x. Okay, and the values are given by that. Now, one thing I want to point out to you, because you will eventually probably get confused, eventually, okay? I will try to point things out as we go here. Now, if your vector is defined as a 200-degree angle here, then everything's going to work out fine. If your vector is defined from the x-axis here, everything's going to be fine. If you always define your vectors relative to the x-axis, then you just apply sine and cosine as is, and the unit circle and the calculations of sine and cosine will just take care of the sines. Everything will be great, okay? But what often happens is the following thing. You might look at this problem. It's totally fine to look at this problem, I should say. Say it a different way. It's totally fine to look at the problem like this, x and y. I'm going to pretend that I didn't know that this was 200 degrees, okay? I'm going to pretend that the vector is pointed down like this, and I know which way it's pointed. Or let me say it a different way. If this angle is 200 degrees, what is the interior angle just to the negative x-axis? Well, if this is 180, then going to 200 means that we know that this angle is actually 20 degrees. So in other words, this is 20 degrees below the negative x-axis. Everything else is the same. The vector has a length of 9. That's all the same. But I guess what I'm trying to say is you can express a vector in different ways, right? In this way, the way that is actually easier to deal with, you measure all the angles from the positive x-axis, so that's 200 degrees. That tells you the vector is going to the lower left. But it's equally fine to say, well, instead of saying it's 200 degrees from the positive x-axis, I'm just going to tell you it's 20 degrees from the negative x-axis. It's still specifying an angle from a different axis, though, from the negative, well, it's still x, but from the negative x-axis down 20 degrees from there. It still specifies the direction of the vector and it specifies the magnitude of the vector. So this is a perfectly fine way to specify the vector. Now, it's more common to do it from the positive x-axis, but in your problems, you might come across a drawing or something that just gives you the interior angle, but you know that the vector is still traveling and pointing in exactly the same way as in the original problem. Now, let's do the problem using this angle, just to see what would happen. Okay, if I use 20 degrees, then c sub x is going to be the same kind of calculation. 9, let's just do it this way, times the cosine of 20. What happens if you put 20 degrees in your calculator and you take cosine? What you're going to get is 9 times, you'll get 0.9396. You multiply by 9 and you're going to get a x component of 8.46. You go back here and say, well, wait a minute. The answer we got here was negative 8.46. They're different. So that worries me. But then let's do the y component. Let's get everything on the board, then I'll explain how to avoid these pitfalls, right? Let's say you use this 20-degree angle over here to calculate the y component. It's the hypotenuse 9 times the sine of 20 degrees, okay? So then you have 9 times, what is the sine of 20 degrees? 0.3420. And so you get, as a result, you get, when you multiply those things together, 3.08. Okay, so you look back up here and you say, well, I got 3.08, but I know the answer is negative 3.08. Here I got 8.46. I know the answer is negative 8.46. It seems that I did the calculation correctly, but I got exactly the wrong sign. Okay, so here's exactly why I'm pointing this out to you. Okay, the thing that you need to remember, it's very important you remember this. When you take an angle and you put it in your calculator and you hit the cosine button, all right, if that angle is, see, we put 20 degrees in here. In the calculator, what am I trying to say? If you put a 20-degree angle into that calculator and take the sine, the calculator is going to assume it's in quadrant 1 with a 20-degree angle above the positive x-axis, because it doesn't know that you specified 20 degrees from a different axis. In the calculator, when you hit buttons and you press it and you say, give me the cosine, it always assumes the angle is measured from the positive x-axis, because that's how trigonometry is defined. So when it was 200 degrees, it knew that it was all the way over here, so it gave me negative components appropriately. That's what it's programmed to do. Okay? That's what the sine function does. But when I stick 20 in there, in my mind, I knew that that 20 was not measured from here. It was measured from a totally different axis much closer, so the number is smaller. But when I stick this 20-degree angle in here, it assumes it's over here, so it gives me a positive x value and a positive y value. These components would be exactly the components I would expect if the vector were here 20 degrees from the x-axis. That would be the x component and that would be the y component if I had a totally different vector pointed this way. So how do you handle it? Okay, here's the rule of thumb. It's actually probably common sense once you see it, but I'm going to give it to you as a rule of thumb. You can use angles interior to triangles like this to find sine and cosine, to find your components, no problem. But once you, in other words, the angle that kind of goes to toward the origin, this angle, you can always use an interior angle like that to find sine and cosine, multiply by the hypotenuse, multiply by sine and cosine to get them. But the numbers you get at the end, you have to compare them to where the vector's actually pointing in space. And you will have to add signs appropriately to make sure. So here's what I'm trying to say. You know that this vector's pointed this way. You know it's pointed to the bottom left because you draw in the picture and it was given to you, right? So if you take sine and cosine, you get numbers down, then you have to make sure yourself that the x component points in the negative x direction. And you have to make sure yourself that the y component points in the negative y direction. How do you know? Because the vector's right here. It's pointed to the left and it's pointed down. So the numbers you get when you use interior angles like that, it's totally fine. But then you may have to add a sign, negative or positive, or you may have to add a negative sign basically, if the vector is actually pointed down or to the left. Right? So in this case, the component is not negative 8.46. The component is, I'm sorry, positive 8.46. It's negative 8.46. And this component is not 3.08. The component is actually negative 3.08. And this is what you would use. All right, so if your vector is defined from the x-axis, or if you've drawn it that way, fine. Just put it in your calculator. It's going to give you the correct sign. It's going to take care of everything. But if you have a vector pointed in a weird direction, they give you an angle from a totally different axis, then you do sine and cosine, you get the numbers, but you have to make sure that the components that you calculate carry the correct sign information. And you do that manually. So you have to think. Vectors pointed to the left, got to have a negative sign. Vectors pointed down, got to have a negative sign. All right? It didn't matter over here because I always got positive answers no matter what I did. But the calculator thinks when you put angles in there less than 90 degrees, it thinks, or it has no way of knowing that the vector's pointed anywhere else. So it thinks it's quadrant 1. That's why it always gives you those positive numbers back. Let's do the last problem. And we'll do it two ways, just like we did it a second ago, just to make sure you understand. So here's x and y. Let's draw our vector down like this. And so we're going to call it D. So we've done A, B, C, and D. And the length of the vector is 4 meters or 4 meters per second or whatever, you know, like this. And let's go ahead and say that we measure all the way around. The angle here is very large, obviously, 300 degrees. Why? Because this is 90 degrees, this is 180 degrees, this is 270 degrees, and a little bit past that is 300 degrees. So that defines the direction of the vector and the distance of the vector, or the length of the vector, the strength, magnitude of the vector. So let's do it the way we always know. We have an angle that's specified from the positive x-axis, so we can calculate the x component as the hypotenuse times the cosine of that angle. Make sure your calculator's in degrees. When you put 300 in the calculator and take the cosine of it, you get 0.5. So the x direction is going to be 2 meters or whatever it is you're measuring. In the y direction, it's going to be the same hypotenuse times the sine of 300. Okay? And so when you take the sine of 300, you're going to get a negative. The negative comes from the sine operation on this, 0.866. And so the y direction is going to be multiplied by 2. You get negative 3.46. Now before we go further, let's see if this makes sense. The whole length of the thing is 4. Right? Most of this vector is actually pointed down and a little bit to the right. So it makes sense that most of the vector should be in the negative y direction. This is very large compared to this, and a little bit of it is pointed in the x direction. So the y direction is larger than the x direction. Secondly, since the vector is pointed down and to the right like this, it's in the negative y direction as far as its y component, so we have a negative sign. That makes sense. And the x component is positive because it's pointed off to the right, so that makes sense. So the magnitudes make sense, and the signs also make sense. You should always check yourself. If you were to go and do the Pythagorean theorem, I'm not going to write it down. If you square this, then square this, add them together, that's going to be the same thing as 4 squared, which is 16. Okay, so you can always verify with the Pythagorean theorem. So that's all good. Let us do it again with the other angle. What if you did it with another interior angle? The reason I bring it up is because a lot of problems will already be drawn for you and they will give you an angle. So right now I'm telling you the angle is 300 degrees, right? But often you'll get a drawing or something and they'll give you an angle in there. So you need to know how to calculate your vector components with different angles other than the easy one from the positive x-axis I'm giving you here. So let's draw our vector in exactly the same location, right? D is equal to, what do I want to do? Yeah, 4, okay? And then let's say that I'm specifying the angle with respect to this axis here. So let's say this is 60 degrees. How do I know it's 60 degrees? Well, because the original angle was 300, and a circle has 360 degrees, so this guy right here must be 60 degrees. So you see how the vector measured with 300 degrees this way at length of 4 is exactly the same vector as measured down 60 degrees over here. These vectors are the same. The numbers might look a little different, but it's measured down from the x-axis here versus measuring all the way around the unit circle like this. So in order to make things a little bit clearer, what do I want to do? I think what I'm going to do is erase this. I'm going to leave everything in place. So this is still x and y. Nothing's changed. I just give me a little space here. I want to redraw this guy here a little bit. I want to take this over here, this triangle here, or this whole triangle right here. I want to kind of redraw it over here. So it's over here like this. So this is vector D. And then let's see, what color do I want to use? I guess I'll use red. So this is a component and this is a component. So this component is dx and this component is dy. So dx is pointed this way, dy is pointed down. And the angle that I'm specifying, that 60-degree angle, is this angle, 60 degrees. So you understand that this situation is written down in triangle form there. The x component of this vector is pointed to the right, that's this one. The y component of this vector is pointed down, that's this one. The angle here is 60 degrees, labeled here. Everything is exactly the same. I just want to redraw it for you so that you can have a little easier time of seeing it. Let's use the 60-degree angle to find the components. dx, which would be the component in the x direction, is the hypotenuse, always the hypotenuse, which is 4, times cosine of 60. Notice that this is a 60-degree angle. Adjacent to this angle is this axis. Opposite of this angle is the y-axis. So sine and cosine still make sense. The adjacent direction is this guy. Adjacent means cosine. Cosine of what? 60 degrees. Okay. Now some of you might say, well, because you've taken some trig, negative 60 degrees, because it's really measured down from the axis. You could put negative 60 in there, fine, no problem. But at the end of the problem, just check your signs and make sure the components come out with the correct signs. So for now, just go ahead and put it at 60 and see what happens. We're going to get 4 times cosine of 60 degrees. Cosine of 60 degrees is going to give me 0.5, same as before. So what I'm going to get, dx is going to be equal to 2. So that's going to be the answer. What is dy going to be? dy is going to be 4 times the sine of 60 degrees. Which is 4 times the sine of, now when you take 60 and you put it in your calculator, what are you going to get? You're going to get 0.866. All right, so you multiply this, whoops, that's not what I meant to write. You're going to have 4 times 0.866 because 4 times the sine of this is equal to this. So dy that you're going to calculate from this guy is going to actually be a positive number. What are you going to get? You're going to get 3.46. All right, so you're going to notice you're going to check yourself. You use the interior angle. You're still using sine and cosine. You check this. Does positive 2 make sense? Well, the vector is pointed towards the positive x direction, so this sign is correct. This sign's not correct. It should have a negative sign because this component should be pointing down. The number is exactly the same, but the sign is wrong. So go ahead and insert a negative sign there and make sure that it's right. And there you go, circle the answer. So the bottom line is, vectors need 2 numbers to be defined. They need the magnitude, the length of it, and they need an angle. Usually the angle in trigonometry anyway is always measured from the positive x-axis all the way around. So I show you how to calculate components of 4 different vectors, one in each quadrant. The main takeaway there is that the components of the vectors can have negative or positive values, and that corresponds to which way the vector's pointed. You should expect to see negative components if it's pointing down, like in the y direction. You should expect to see negative x components if it has anything cocked over toward the negative x direction, right? Now, separate from that, in most physics problems, you'll have a diagram. Right? It'll have like a wedge or something, or some kind of angle trajectory, and they'll label an angle there and they'll say find theta. Or they'll give you the angle, 44 degrees. So oftentimes in physics, the angles aren't given to you measured from the x-axis like this. Usually they'll draw something and they might give you an interior angle. So you need to be comfortable with finding the components of vectors given different angles defined differently than the ones I'm telling you here. So I guess what I'm trying to say is you just make sure the angle that you're using, that the opposite side to that is the y component, and you make sure that the adjacent side to that is the x component, and you're good to go to use that angle. You take the cosine and the sine of the angle as usual, multiply by the hypotenuse as usual. The numbers you get, absolute value-wise, will be correct. But then you go back and look and say, does it really have a positive x component? Yes. Does it really have a negative y component or a positive y component? No, I got to add one. The reason is because when you stick 60 degrees in the calculator and take the sine, it assumes the angle's up here, because it's always going to assume a positive number. It thinks the vector's up here, positive x, positive y, but the vector's not, it's down here. The magnitudes are the same, so you have to insert the minus signs for the components as needed. All right, so make sure you understand this, solve these yourself, go on to the next lesson with me. We're going to get more practice with calculating vector components. Learn anything at mathandscience.com.